The next thing we talked about in class is physical and chemical properties. So remember, physical and chemical properties is something we talked about in our second unit of first semester, and so you can go back and watch some videos about that. But we're going to list some physical and chemical properties of acids and bases so that we can learn, okay, what are the differences between these two things, or how are they similar? And so an acid tastes sour. So anything like a lemon, sour candies, citrus fruits, they all taste sour, and that is an indicator that there are acids in them. Okay, and a base is going to taste bitter. If you've ever gotten soap in your mouth, you know it has a really horrible taste, and that's kind of that bitter taste there. The base is what's making it have that taste. And an acid is going to feel like water. If you were to get vinegar on your hand, it would just feel like normal water, but it would smell like vinegar. And a base, when you get it, when you touch it, it feels very slippery. This is what gives soap or bleach or any kind of cleaner that kind of slippery feel is the base that is in it. Now, acids and bases are both ionic compounds. And so this means conductivity, right, which measures the ability to let electricity flow. Electricity can flow, and all ionic compounds are good conductors. So because an acid is ionic, it is conductive. Okay, and because bases are ionic, they are also conductive. And we'll talk about in a later video how to tell whether or not an acid is a better or worse conductor compared to another acid or another base. And it's dependent upon their strength. Now, when we talk about reactivity with metals, acids are extremely reactive, so very reactive with metals, which is why they're not used in drain cleaners, because if you cleared out the clog in your drain, but you also had the acid eat through a hole in your pipe, you're now going to have a lot more problems in your house than just a clogged drain. Whereas bases do not react with metals. Okay, and that's the key thing, is this is talking about with metals. They're both very reactive with each other and other things, but bases do not react with metals. Now, blue litmus paper. If you take blue litmus paper, which we did a demonstration of this in class, but you can also look it up on YouTube and find some videos of things. Blue litmus paper, when it's dipped into an acid, will turn red. Okay, but if blue litmus paper is put into a base, it will stay blue. Okay, and that's going to be a key thing, is blue starts with B, and so does the word base. Now, red litmus paper will stay red in an acid, and it will turn blue or a purplish color in a base. Now, here's the key thing. The only thing that these litmus paper can do is tell you whether or not it's an acid or a base. It can't tell you the specific pH level. We're going to talk about pH paper and pH indicators that will do that. This will only tell you acid or base. Now, there are two types of acids and bases. And the first one was the first definition of an acid and base came from this guy named Arrhenius. And this is just his last name. So if you're like, man, what does that word mean? You don't know what it means because it's this guy's name. And so what Arrhenius said was, he said that all acids, they dissociate, which remember, we learned about that word when we talked about how ionic compounds dissolve in water. So when an acid is in water, it dissociates or breaks apart. Okay, you got to remember what that word means. And it would help if I could spell the word apart. It breaks apart into H+. That's one of the things it produces. When it dissociates, H plus is one of the things that it makes. But he said that when bases dissociate or break apart, they dissociate into OH minus, which the name of OH minus is on the back of your periodic table. It's a polyatomic ion that we learned about, and its name is hydroxide. Okay? It produces hydroxide in a solution when it dissociates, when it dissolves. And so some examples of Arrhenius acids are nitric acid, hydrochloric acid, hydrofluoric acid, water. Okay, now a key thing about water is water can be rewritten to say HOH. And that means it has the hydrogen in the front it needs to be considered. Sorry. It has the hydrogen in front that it needs to be considered an acid, but it has the OH it needs to be also considered an Arrhenius base. And so Arrhenius bases, because they produce hydroxide in solution, could be something like calcium hydroxide or sodium hydroxide, lithium hydroxide. Any of the hydroxides are going to be considered bases. Now, this definition worked for a long time, but then two different scientists, Bronsted and Lowry, so these are the names of the scientists who came up with this new definition. They noticed that there were some substances like ammonia, NH3, that behaved like a base but could not be included in the Arrhenius definition because it did not make OH. And so they said, we need to expand our definition of a base in order to include these other things that have the same physical and chemical properties. And so they changed their mind about, well, not changed their mind, they just kind of changed the world's mind about what could be considered an acid and a base. They said an acid is actually something that donates H plus. Right? It's not that it just necessarily produces H plus, but that it's donating that H plus to the base, which is going to accept H plus. And this is what we read about in the comic and in the previous video. Now, so some examples of Bronsted-Lowry acids are HNO3, HCl, HF, H2O. There's no difference between Arrhenius acids and Bronsted-Lowry acids. They are the same. However, the bases is where it is different. In a Bronsted-Lowry definition, ammonia is considered a base because it can accept an additional hydrogen. But NaOH, LiO, so sodium hydroxide, lithium hydroxide, water, they are all still considered bases. So the Bronsted-Lowry definition took what was classified as an acid and base and expanded it to include more chemicals. And so this is why water, which this is a really important vocabulary word for you, is considered amphoteric. It can be an acid or a base, and I'll show you how. When water, which is H2O, is behaving as an acid, that means it's going to donate hydrogen. Okay, so when it donates a hydrogen, it produces OH minus. Okay, so in this case, water is behaving as an acid, and OH minus is the conjugate base that it produces. The conjugate base. Now, when water, however, is behaving as a base, that means it accepts or receives an H plus. So instead of giving one away, it's now going to have an additional one, and it becomes H3O plus. And so this means that water is a base, and H3O plus is its conjugate acid. Now, H3O plus is again on your polyatomic ion list, but it's called the hydronium ion. And that is a name you're going to need to be familiar with. You're just going to need to know it. And so one thing to keep in mind, is water is both acid and base, but OH minus is a base. H3O plus is an acid, very clearly. They cannot be both. They are the product of when water behaves as either an acid or a base. Okay, and it can do both. Now, when we talk about pH, okay, you should have learned about this in physical science, but pH, the H stands for hydrogen, or H+. The OH stands for hydroxide. And so the P that is in both of these stands for potential. So this means that when you're looking at the pH range, you are measuring the potential amount of hydrogen, or hydronium ion. Remember, H3O plus is hydronium, okay? And it's measuring how acidic it is. And sometimes we just say it's measuring the H plus instead of H3O plus ion. And when you're looking at a pH scale, an acid will be from 0 to 7 on the scale, and a base will be from 7 to 14. Now notice 7 is in both, and that's because 7, a pH of 7, is neutral. It's in the middle. It's neither an acid nor a base. Now with POH, it's measuring hydroxide ion. It flips. A base, or an acid, excuse me, is from 7 to 14, and an acid is from 0 to 7. Now the reason why this switches, and I want to be very clear about this, is that when you have an acid that has a pH from 0 to 7, it's measuring your H+. This means you have lots of H+ ions in your solution, whereas 7 to 14 means that you have few H+. And same thing here, if you're 0 to 7 on a pH scale, this means you have lots of OH minus ions, or hydroxide ions, whereas 7 to 14 means that you have few hydroxide ions. And I know that you might think, Ms. Nichols, this is backwards. If I have 7 to 14, that's higher than 0 to 7. Why is it that there are so few? And that is because the calculation for pH, to actually calculate it, your pH is considered the negative log of your H+ concentration. And so I don't know about you, but negative logs are a pain. But essentially what happens is if you have a high number, you end up getting a low answer, and vice versa. And so that's just one thing to keep in mind. And we will talk about pH much later. But you really need to know the range and conceptually what that means about the amount of hydrogen or the amount of hydroxide ions that you have. Now, this word here, phenolphthalein, okay, that's how you pronounce it, phenolphthalein. Took me many years to be able to write it without spelling it wrong. Well, phenolphthalein is an indicator, and that, again, is another one of our vocabulary words. And an indicator will change color based on the pH. We did a demo including this in class. You can also look at a lot of videos on YouTube that are very, very colorful. But phenolphthalein, when it is in an acid, will be clear. Okay, but if you put phenolphthalein into a base, it will be bright pink. And so there's a technique called a titration, where you're adding an acid into a base or a base into an acid, and what you're trying to do is make the phenolphthalein that's in there become a very, very, very pale pink. And that will mean you're at a pH of around 7. And so different phenolphthalein will change color at a specific point, just like other indicators have a specific point where they change. And so all you know is that it's either higher or lower or right in the middle of that range. And so these are the properties of acids and bases, or some of the properties of acids and bases, a real good summary.